All right, so we're back with the second part of probability. So today we're going to talk about the mean or expected value. And so we're going to show the process of going through this on how to build this up, and then go over an example or two to demonstrate the process. All right, again, for the previous one, we talked about what a probability density function is. A probability density function is one whose function is greater than or equal to 0 for all values of x on a particular interval, whether it's from negative infinity to infinity or some set interval. And then the area underneath the curve is exactly 1 on that interval. Okay, so mean and expected value. So let f of x be a density function that represents the so here we're going to go over specific examples, so then that way we're still going to build a generalized version of this, but to give a specific example helps. Otherwise, then the notation gets kind of weird. So that's why we're going to look at a specific one. So again, let f of x be a density function on AB that represents the on-hold time a color waits. Okay, so that's what x is going to represent, is the hold time. All right, and n is the number of colors in the sample. Okay, so what we're going to be looking at, just to give a graph, and here I'm just going to generate some particular function here. And we're going to assume that the longer time people wait, the less people that are waiting. Okay? So here's our interval from A to B. Okay? So this is our function that we're going to be looking at. All right? So this is our f of x. So first of all, we're going to divide AB into n subintervals of width delta x. So does that sound familiar to every single thing that we've dealt with before? All right. The probability that a person falls into category from x of I minus 1 to x of I. Okay. And here we're just going to represent this in red so that way we can have a distinguished look between the two. And I'm going to exaggerate this, but this is what we're going to be doing on every single piece of this. So here we're on some subinterval. Is the area underneath the curve, f of x, from x of I minus 1 to x of I, which is approximately equal to f of x of I star delta x. So f of x of I star, again, is the midpoint. So I bar. And so what we're doing is we're saying, well, the probability, and whoops, the probability that we're looking for, or that a person falls into this category, is the function value and the width of the interval. So again, the area of that box that we've created. Okay? So that's what this is representing. This is our probability that somebody falls within this category. Okay? All right. So if that's the case, again, this is our midpoint. Then, out of our sample of n people, the number of people who lie in this category, or this interval, from x of I minus 1 to x of I, is what? Well, if we know the probability that somebody lies in this group, we just multiply by the number of people in this sample. Okay? So, and that means it's just simply n times f of x of I bar delta x. Again, think about that. If we had a certain interval that would, say, 5 to 10 minutes, and the probability that somebody is in that group is 60%, and we had a group of 100 people, that means 60 people would lie in that category. That's what that would mean. Okay? So that's where this number is. So n is the number of people. F of x of I bar delta x is the probability. Okay, so this would equal the number of people in that interval. All right. Well, we could then figure out the total time that this group of people waited. Okay, so again, think of this as a very, very small interval that we're dealing with. So everybody's going to approximately wait the same amount of time. So again, this is an approximation. So the total time this group of people waited is simply the product of the time times the number of people. All right? And we're going to do this across the whole entire board from A to B. So that means the approximate total of everybody's wait time is just adding all of these subintervals together, which is a summation symbol. As I goes from 1 to n of x of I bar n f of x of I bar delta x. Okay? So this is the approximate total of everybody's wait time. So if we looked at a group of 100 people, we calculate the wait time that they had, and that's all this is. All right. Well, now let's talk about calculating the average. Well, we're just going to divide by the number of people. Okay? So, if we divide by the number of people, let's rewrite this real quick. N is some constant value. I could pull that outside of this summation. Well, if I divide by that, that means my average is simply equal to the summation as I goes from 1 to n of x of I bar, f of x of I bar, delta x. And as we apply a limit, as n approaches infinity, we're going to get the limit as n approaches infinity of the summation as I goes from 1 to n of x of I bar, f of x of I bar, delta x, which becomes, well, we've seen this before. This is our limit definition of an integral. Well, that's the integral from a to b of x, f of x, dx. And this is how we calculate the mean or expected value. Okay? So here is our definition. The mean or expected value of x is, and here we're going to give it a name, we're going to call it mu. So that's the Greek letter. It's the integral from negative infinity to infinity of x, f of x, dx. So this is also sometimes called the average value of x. All right. Now this is, you want to keep this separate though. So this is the average value of the continuous random variable. This is not the average value of a function, which is back in chapter 7. So make sure that you keep that separation. Again, this is the average value of the variable, not the function. Okay? So again, this is just the Greek letter mu. So if you've seen it before, that's great. If not, this is a new Greek letter for you. Looks like an M or a U, depending on how you write it. But it looks like has a elongated tail on the left-hand side. All right. So let's put this to practice. So so in this particular example, REM sleep is the phase of sleep where the most active dreaming occurs. In a study, the amount of REM sleep during the first 4 hours was described by a random variable t with a probability density function as follows. Now this is, again, what does it mean for it to be a probability density function? Well, the area underneath the curve has to be equal to 1, and it has to be positive and or 0 on its whole entire interval. All right. let's first find out a few things. I want to find the probability. So here, that way we can work with some values and actually work with this guy. So I want to find the probability that our variable t, that is our time, is between 30 and 60 minutes. All right, so I want you to take a second, see what you need to do in order to do that. Okay, so since we are dealing with the probability, since we're dealing with a piecewise defined function, notice we've got to be careful on how we calculate our probability. So notice we're going between 30 and 60 minutes here. Well, that means we're going to be using both functions. So we have to separate this out. So we're going to have an integral from 30 to 40 as 1 over 1600 t dt, plus the integral from 40 to 60 of 1 over 20 minus 1 over 1600 t dt. All right, so now we got to walk through the process. Well, the nice thing here is this is going to be real quick for our antiderivatives because it's a polynomial. We do have some fractions, but that's okay. We can deal with that. All right, so our first integral here is going to be 1 over 3200 t squared evaluated from 30 to 40 plus, and here I'm going to put this in brackets just to keep it separated a little bit, 1/20th t minus 1 over 3200 t squared, and it's going to be evaluated from 40 to 60. All right, so when we plug 40 into here, we're going to get 1600 over 3200 minus 900 over 3200 plus, and now we're going to deal with this one, 60/20 minus 3600 over 32 minus 40/20 minus 1600 divided by 3200. Good thing is we can simplify a lot of things here. Okay, we can cancel out a lot of zeros to help us out. So we'll get 1/2 here minus 9/32 plus, all right, here we're going to get 3 out minus 36 over 32. And here we can cancel this one out and get 2 minus 1/2. So this is going to boil down and simplify to 19/32, which is a little over 51%. Okay, so that's all you have to do. So nothing horrible there, very straightforward. Okay, next thing, we're going to deal with B. So I didn't tell you what B is, but here, B, I want you to find the mean. All right, so take a second, go back to our definition here, and I'll scroll up. All right, what does it mean to be the mean? The mean is equal to the integral from -infinity to infinity of x f of x. All right, so now that you have that, take a second, pause the video, and try it out on your own. All right, so we're back. So here, you got to be careful. Our mean is from 0 to infinity of t f of t dt. All right, again, going back up here, the reason I know it's from 0 to infinity is for we have 0 to 40, 40 to 80, and then otherwise. So we're not dealing with negative time here. That does not make sense. So our interval is from 0 to infinity, okay? Which means that we're going to have to write this out a little bit further. Okay, so we're going to have the integral from 0 to 40 of 1 over 1600 t times t, so t squared over 1600 dt, plus the integral from 40 to 80 of t over 20 minus t squared over 1600 dt, plus the integral from 80 to infinity of, well, the nice thing here is our function is equal to 0 everywhere else, so 0 dt. So the really nice thing here is we're only dealing with these two integrals, all right? But again, you have to have this proper setup to get there. All right, so the antiderivative of t squared over 1600 is going to give us t cubed over 4800, evaluated from 0 to 40, which is great because plugging in 0 is always nice to have, plus the antiderivative of t over 20 is t squared over 40, minus t cubed over 4800, and evaluate that from 40 to 80. All right. We are going to get some big values out of this. That's okay. Sometimes you will have to deal with that. All right. So 40 cubed, so there's going to be 3 zeros there. So we are going to get 64,000 out of 4,800. All right. And then plus our big values here. So that was the nice thing about this one. We had a 0 to deal with. All right. All right, so 80 squared is going to give us 6,400 divided by 40 minus 512,000 divided by 4,800 minus, and now everything evaluated at 40, 1,600 divided by 40 minus 64,000 divided by 4,800. Good thing is we can reduce a lot of things down. And we are going to get 120 minus 2,400, or 240 thirds, which reduces down to 120 minus 80, which is equal to 40 minutes. So the average time a person spends in REM sleep is 40 minutes. Right, and that's it. So the reason I went over a more complicated one is because it's easier to deal with. If showing an easier example would be very, very easy to deal with. So that means all you're going to deal with this one is multiply the function by its variable and then evaluate. And that's all you have to do for the mean. And that's it. That finishes our section of 8.5 with probability. The next sections that you'll be looking at is 11.1, starting with sequences, and then getting on into series after that.